Hi guys, welcome to the 8th tutorial of the Embedded Systems course. This tutorial we will be talking about serial communication data transmission protocol, which is UART, which stands for Universal Asynchronous Receiver Transmitter. This UART serial communication consists of 3 channels. It's a serial communication, as I said before. It consists of 3 channels. If we have two microcontrollers, as we can see here, we have 2 main channels for data transmission. We have 2 separate channels. Unlike the I2C, I2C had 1 channel, bidirectional channel, but here in the UART protocol, we have two channels for data transmission. Descending channel is called TX, is connected to the RX, which is the receiving channel on the other side of the on the receiver side. So the sender side is the TX, is connected to the RX on the receiver side, and the RX on the sender side is connected to the receiver TX side, because we send data from microcontroller 1 via the TX to the microcontroller 2, and it's received via the RX. And whenever we want data from a microcontroller 2 to microcontroller 1, we use it from the TX to the RX. And we have the common ground because we need both of them to be in the same circuit, as we said before. So in this communication protocol, we don't have a direct clock wire, but we have the baud rate. That's we always do like serial.begin 9600. This is the number of bits per second a UART device can transmit or receive. Okay, so the baud rate is the frequency of the sent bits per second. Okay, so the UART uses the baud rate on both sides, as we have said before. Microcontroller 1 has to have the same baud rate as microcontroller 2, because we need to send the data now with no clock wire, with no direct clock wire. But sometimes we can see USART or UART, which is right, which is wrong. What is the difference between both of them? It is simple. USART is a universal synchronous asynchronous. It has the same, it has 2 modes, not just asynchronous, it has synchronous also, receiver transmitter. It is a microcontroller peripheral that converts incoming and outgoing bytes of data into a serial bit stream. While as we introduced UART minutes ago, is a universal asynchronous receiver and transmitter. It is a microcontroller peripheral that converts incoming and outgoing bytes of data into a serial bit stream. So what is the difference between them? Simply is the serial data may be clocked. Okay, so in the USART, the synchronous mode has a clock. When we work with USART on Arduino, we have an extra pin, which is called XCX. When we connect to this bit, this has a clock at which now microcontroller 1 and microcontroller 2 are working on the same clock, and we send the data via the clock, not just via the baud rate. So the USART, in a nutshell, the USART, we can use the baud rate in the asynchronous mode, or we can use an external bit which represents the clock to synchronize our data transmission. Coming to the second part of the tutorial, introducing polling versus interrupts. Polling versus interrupts, they are 2 different approaches to writing our code on the Arduino board. Simply pulling, in very simple words, pulling the code does not do anything until our hardware or our input-output devices have some kind of input, and then the code takes the data from the, reads the data and then works with it, while the interrupts, our code is running fine and perfectly, and whenever our device is receiving any kind of input, it interrupts the main program. We go to the ISR, interrupt service routine, deal with this kind of interrupt, and then go back to wherever we stopped executing our code. So think about it. If you're going going for a run and we are expecting a call, we have two approaches for this particular call. If we tried the pulling approach, we won't start running until we take the call, deal with it, and then run, while the interrupt, if we have our approach in the interrupt form, we will go for the run, and whenever we receive that call, we stop, take it, and then continue running. So we can say pulling, we will introduce it in a bit more detail. So pulling, it's a protocol at which the CPU constantly checks on our hardware, constantly, wasting countless processor cycles until the device change its status. It is mostly used with input-output devices, which we require some kind of operation from these kind of devices. The CPU waits for the input-output device until it's ready and expecting a reading from it, not going to execute anything until the reading comes, and the device, the input-output device, is serviced by the CPU. Okay. While the interrupts are hardware mechanism, as we said before. Our code executes normally, so these interrupts can take place at any time while our code is executing fine. So when our device, our particular device that has the interrupts, takes or reads an input, this device notifies the CPU that it requires the attention because we are reading something, please deal with it. So the CPU gets an interrupt signal, it stops the current process and responds to that particular interrupt by passing the control to the interrupt handler, which services device, which is the ISR, because the interrupt service routine deals with that kind of interrupt. So bottom line, the device is serviced by the interrupt handler, at which the interrupt service routine identifies the interrupts and accordingly deals with that kind of input. We can have software interrupts or hardware interrupts. There are multiple types. So we can have, in short, pulling versus interrupts. The main difference between both of them, the interrupt and the pulling, is that in interrupt, the device notifies the CPU that it requires its attention, while in pulling, the CPU continuously checks the status of the device to find whether they require attention or not. In brief, an interrupt is asynchronous, whereas pulling is synchronous, right? Because pulling is each clock cycle we check the device, check the device, but the interrupt happens wherever. It doesn't have to happen with the syncing with the clock. In question 1, in this exercise, you will implement a polling based RX task T1 for UART communication. T1 is a low priority continuous task. You will also create a periodic TX task 2 that has the highest priority and prints out the character typed by the user on Arduino serial monitor if and only if the character is H. So in this question we will merge the two concepts of the tutorial. The first concept is the UART serial communication. So we have two tasks, tasks 1 which is a receiver task and task 2 which is the sender task, TX, and we will implement this code via the polling protocol, which constantly checks our input-output device for any changes until it reads whatever data from this input-output and then executes its actual code. So here the T2 sends whatever the user sends a letter to T1, which is the letter H, whenever the user types it on the serial monitor, if and only if. If we typed another character, it won't type anything. We just want to send from task 2 to task 1 the letter H, if and only if the user enters it on. Coming to our code now, this is the code for this question. First, we said that we have task 1 and task 2. We include our Arduino FreeRTOS library and the semaphore library too. And we create a semaphore because we were not allowed to go to task 2, task 2 unless task 1 receives the desired letter, which is in ASCII. The capital H in ASCII is 72. So whenever the task 1 receives the letter, it gives the semaphore to task 2, and task 2 prints it on the serial monitor. So step by step, we need to define our semaphore of sem of type semaphore handler underscore t, and we have task 1 and task 2 with their parameters. We have a variable to save the data we read from the serial monitor. And in the setup, we begin the serial communication with baud rate of 9600, and we create our binary semaphore. We don't need a mutex. We will use the binary semaphore, and the counting semaphore is useless in our case here. And then we create task 1. As we said before, it's of low priority, and task 2 of higher priority. And as we know that the scheduler starts automatically and we don't have anything in the loop. Task 1, on the other hand, checks the serial monitor if it has any kind of input, and whenever we have something in the serial monitor or the wire itself or the communication channel, if we have anything, we read it we read it and then save it in the upcoming incoming byte, and then check on its value if it is H, capital H. 72 is capital H in ASCII. So we give the semaphore away, and then comes task 2. We have a delay of 1 second, which is 1000 milliseconds. And in our while loop, the first thing that the task does is taking the semaphore and writing the incoming byte, and just like that's a space, and then goes to sleep. Okay, so we need to upload this on the Arduino board. It's compiling. Yeah, it's taking some time. The code is compiling now. Should have done that. It's okay. We have all the time. So the code is compiling. Still compiling. Move. Okay. It's uploading on the board. Done. So we launch our serial monitor. Uppercase, we write L, nothing, O, nothing, P, nothing, H, types H, M, nothing, N, nothing, V, nothing, B, nothing, lower caps H, nothing. It just checks for the uppercase H. So we can clear the output again and close it, open it again. As we can see that the code does not do anything and does not type anything until it receives data from the user through the serial monitor. Whatever data we write, the CPU takes care of it, and it expects some kind of input, which is H, uppercase H, and then it types it, or it prints it out. We can just take whatever the user inputs in the serial monitor and prints it out, but we want a particular letter, which is H. U doesn't do anything, L doesn't do anything, M doesn't do anything. We want a particular thing, not just whatever the user writes in the serial monitor, but we can see the idea that the CPU doesn't do anything except for checking on the serial monitor, as we can see here in the task, that we are checking the serial if anything is available on the receiving side. Is there anything? Or on the communication channel, if there anything. Okay, if there anything, as we can see here, or we saw earlier, we have something. We have an H. Yeah, that's what we want, which is the 72. Yeah, give the semaphore to task 2 and then print it out. If not, no, I'm not gonna do anything about it. No, I'm just gonna print the H only, and I'm just gonna print only if and only if the user enters the H. Task 1 here is an RX task, which is a receiver task from the serial monitor, and task 2 is a TX, which is a sender task to the serial monitor. So it's not that they talk to each other or send to each other. It's an RX based task from the serial monitor, because it reads the input from the user from the serial monitor, and task 2 is a TX, which is a sender task, because it prints out the H on the serial monitor. Going to question 2. In this exercise, you will implement a new ART interrupt-based program that toggles the debug LED whenever a user enters a character from the serial monitor. We will use the data sheet and the header file called interrupt. So now the previous question was implemented. It was a UART program, but it was polling based, which means again that the program is it's on hold until we deal with our input output, which was from the serial monitor, and then we execute our code. But now we want to implement an interrupt based program, which means that our program works fine, but whenever an interrupt comes, it stops in the middle, and then we go to the ISR, which is the interrupt service routine. It deals with the interrupt, and then we get back to wherever we were stopped by the interrupt. Okay, so first we need to understand that we have the interrupt from the serial monitor, which is a character entered by the user. So we need to identify the kind of interrupt, which is a hardware interrupt. Okay, it's a receive interrupt, and then go and identify our interrupt service routine. So now we will solve the problem in embedded C. So since it's embedded C, we need to set the registers directly, unlike the Arduino C. But now we need to go to the formula sheet, because the USART has 3 control and series registers: USART control and series register A, controller and series register B, and control and series register C. Register A mainly has the status bits, like the 7th bit, the receive complete, transmission complete, data register empty, the frame, if there is any error in the frame, data overrun, parity error, transmission speed, and communication mode. So register A mainly is a status 1, more than setting things, which is the control word in it. So we will be using in this problem, in this solution, we will use register B and register C. Okay, but before that, we will just climb back to the solution and try to understand these definitions. First, we will define the transmission speed of the CPU, which this is the variable name, and we now have value in this variable name. We end it, and then we have a variable called FOSC, which holds the value of the transmission. And now we want, as we do in the Arduino C, we say serial.begin, and we set the baud rate. We need to do this here, but it's a bit tricky in the embedded C, because it requires multiple steps, because here the myUBRR register is the register which holds the value of the baud rate, but we cannot hold it. We cannot directly set this value to that register. To that register. So this is the baud rate that we want, but the myUBRR, whatever is saved inside, is from this formula. Okay, this is the frequency of oscillator. So the formula is meaning that this is the baud rate that we want, right? So we put this in quite a formula, and this formula produces some kind of value or output. So this value is saved in the myUBRR, and then it is reversed engineered inside the code. We don't know how it's done, but it's like it's from this equation, but we don't care how it's done or which at which stage, where, when. We don't care. We need to understand that in Arduino C, we just say serial.begin, and we put the baud rate, and that's it. But here in the embedded C, we need to write this formula, okay, which is the frequency of the oscillator, which is this value, over 16 is the transmission speed. Okay, if we want double the transmission, so we will go for 8 or 4 more. okay, and then times the baud rate that we have, sorry, this is the value that's here, yes, okay. This, after we compute it, we have our let's say it's an x variable. This x variable has a value from this equation, and then it is saved inside the my BBR, what would I have no, sorry, my UBRR. It is saved inside, and then within the code to have the 4800, it reverses this equation, and then it works fine. Okay, so the first information that we need to understand, that in embedded C, the UART baud rate is not assigned directly, it is assigned through this equation, which is the frequency of the oscillator, this one, over 16 times the x plus 1. Okay, here, this is the reversed engineered version. Okay. Okay, so when we put this and this, it's just done. It's a bit tricky, but it's okay. Okay, so now we have the frequency, transmission rate of the CPU and the baud rate, and then we want to start the code. But first, we need to include the input-output header, because we have input from the serial monitor, and then we have delays, that's normal, and the last but not least, we have the interrupts.h. What is that? We will know in a few seconds. But first, we will go to our main method, which is this one. Okay, it calls this method, which is usart underscore init, and it passes the value of the baud rate, and then what it does, it sets the debug LED. It is pin 13 in Arduino C, but in embedded C, it is in port B, pin 5. So we are setting it to be 1 as it's an output, because the LED will change, right? As we said in the question, that whenever the user enters anything from the serial monitor, the debug LED will have to toggle. So here, here in the main method here, we ORed the value for pin number 5 in port B to indicate that our debug LED is an output. And then we are enabling the global interrupt. Remember in tutorial 3, we had the status register bit I, which was bit number 7, which was the global interrupt enable. We said that now we are trying to have this code in interrupt-based program. So we need the code to accept external interrupts, because if we did not write this one and the user enters something through the serial monitor, and we don't have this one, so the board suppresses this interrupt. So we need the code to act upon the interrupts which it receives. So we are enabling the global interrupts, that when the user enters anything through the serial monitor, so the global interrupt goes and calls the ISR, and ISR meaning that it has the power to stop the actual code and implements its own thing, and then goes back to the main code wherever we stopped. Okay, that's the whole idea behind this line. Okay, and then while 1, because it's forever, it's an infinite loop, and then return 0. Okay, so this is the first part of the code, which is the main method. So we will go up and see the method which the main method calls, which is called usart underscore init, and it gets the ubrr. Okay, a variable يعني. Okay, so the first step is to get this value to the ubrro high and low. We have a register called ubrr high and low, which we set the baud rate through. Okay, that's a bit confusing. No, here in C, okay, here in C, we cannot set the value directly. Okay, so in order to have in embedded C and working with Arduino, we need to work in that particular pattern, that our baud rate, it's not directly saved in a variable. No, it has to be saved through some kind of an equation, and internally it reverses it and gets our original value, and then it saves it in the registers which are responsible for the baud rate. And we can go back to the formula, what's called data sheet. Okay, and that it is, yeah. Okay, yeah, and yes, yeah. The USArt baud rate registers, we have 2, because we can have multiple values for the baud rate. We can have the 4800, that's the one here, and the most common one that we use, which is 9600. We can have 11500. It's really we can have a large number of baud rate, so we need some kind of a bigger register. An 8-bit register is not enough, so we have two 8-bit registers. We use the first one fully, the low one fully, and the upper one, the first 4 bits of it. Okay, so this is what we are doing here. The low register of the baud rate, we set the ubrr variable to it, so it took the first 8 bits, right? Like we can see here, right? So we are left with the 4 bits which were cut, because the ubrrol supports only 8 bits and we have 12. So we shift the remaining 4 to the right in order for the high register to take them. Okay, the low register, let's imagine with me that we have here 8 bits and we have here 4. All the 8 bits were saved in the low one, and we have these 4 out of reach of the high register. So we need to push them to the right by 8 for the remaining 4 bits to be caught by the ubrr H register. Okay, so we set the baud rate in the first step. So now the second step, we will go back to the second register of the Arduino USArt, which is the Arduino USArt control and status register B. We will set two bits only, because we are receiving, not transmitting. In this case, we are receiving, right? So we will go and enable the interrupt, the RX, which is the receiving, complete interrupt enable. Okay, meaning that writing this bit to 1 enables interrupt on the RxCN flag. A USArt receives or receive complete interrupt will be generated only if the RxIEN bit is written to 1, the global interrupt flag is in SREG is written to 1, and the RxCN bit in USRNA is set. Okay, we don't need to talk about this. We are saying that now we are enabling the interrupts through this pin, through receiving via the USArt. Okay, so again, not just this, which is here, we need to enable the transmission itself. So we are enabling the transmission. So like we are saying that, okay, now you are receiving and you are receiving also its interrupts. So we are allowing the receiving to happen, and we are allowing the interrupts of the receiving to happen again. So we can have whatever the user enters and trigger our code to deal with it. Otherwise, it will be suppressed and not dealt with. We will not go to the ISR. That's the whole thing, okay? So after enabling the receiving and its interrupt, we will go and set the size of the data of our register to receive the data. So now we don't do this in Arduino C, right? I don't think we do that. But we don't do that. In embedded C, we do it. So these bits are found in the third one. Okay. The USArt control and series registers NC. We will go down, 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 and we have these 2 bits, right? Oh, they are actually 3. There are 2 bits here, and the third bit is in here. Okay, but it has an initial value of 0, as we said before that in the data sheet we have the initial value of the register. We have here it says 0, and we can set the character size up until 9 bits. Okay, we want it to be 8 bits. So this is the bit which is in register B, not in this register. We are talking about register C. So this is in register B. Okay, so we want to have 8 bits. Accordingly, we will be having these 2 bits to be 1 and 1. We can see it here in the code, right? Okay, and 0 in the bit which will it could be found in the second register, and it's already 0 because this is the initial value. Okay, so now we understood the main method, which is the normal method. It calls the, let's say this is the setup. Remember in the Arduino C we have the setup and the loop. This is, let's say it's the setup, this is the setup method, which is here up until here. We are setting the baud rate through the register itself, and we are enabling that we are receiving, not transmitting, and enabling the interrupt of receiving, plus we are deciding on the character size, whether it can be 5 bits, 6 bits, 7 bits, 8 bits, 9 bits, whatever we want, but here we want it to be 8 bits. So yani, that's it. Okay, meaning that now whenever the user enters a value, a keypad, enters anything through the serial monitor, we will have an interrupt. So in that particular manner, we will go to the ISR, which is interrupt service routine. So the interrupt service routine has one parameter only, which is called a vector. A vector here, in any system you have multiple interrupts or hardware interrupts. You can have multiple input outputs peripherals, and each and every peripheral you deal with it differently. So you need the ISR to understand which method belongs to which interrupt. You understand? So now we are trying to write an interrupt service routine method. First of all, the ISR, the name of the method does not change. If we have 5 interrupt types, we will have ISR 5 times. It's not like this one, we can change it and the main does not change. No, the ISR, let's say it's like the main method, it does not change. Okay, its name does not change, because if we change the name, it won't recognize it, as this is the one that we need to execute because an interrupt has occurred. So, as I said before, we can have multiple interrupts from different peripherals. So once the interrupt happens, the CPU goes and matches the vector of the interrupt. Okay, so here we have a USArt underscore RX underscore vect. This is a USArt interrupt, which is a receiving interrupt vector. A USArt receiving interrupt vector. Okay, so this can be found in the interrupt header, which we will try to talk about here. We have here the vector name of whatever interrupt can occur, which can occur on our boards. Here the ADC vect, which is ADC conversion complete. That's an interrupt for finishing the ADC conversion. In tutorial 5, we had the ADC in a polling manner, right? We kept on checking on the bit which says that the conversion is complete, right? Or start conversion bit. Whenever this bit is 0, the conversion, what happens? It finishes and we can deal with the data after conversion. But now, if we want to have it in an interrupt manner, we will have the ISR function, and the vector name is ADC underscore vect. Okay, when we have this, meaning that our conversion is complete, and then in the method we will have whatever we had in the method back in that tutorial, that we saved our data into a new register and we converted into values in volts. Okay, so we have all types of interrupt vectors in the boards and the compatible boards also, because we don't have just Uno, we have Mega, Uno, we have Nano, we have multiple types of Arduino based what we say, boards, Atmega boards. We have multiple Atmega boards, so we have different types of interrupts which are compatible with some kind of boards. Yeah, and that's it. Okay, so we had our USArt underscore RX underscore vect, which is this is the description of the of our vector, which is USArt RX complete, that we received something, we need to go and deal with it. Okay, so this is the receiving register. Let me try to get it here. This is the register which we have the data from the, okay. So we received something through the RX, so it is saved or it is read using the UDRN register. Okay, and then we have it in another variable because we need to work with it. or whatever, read it. We just need to move it because otherwise it will be overwritten and we will miss our chance. Okay? And then after we received something, we just are storing it in a variable, and then we are toggling XOR the debuglet. And that's it. Okay? So bottom line, the embedded C interrupt based program, how it works. Our code works fine. We are not waiting for the interrupt to happen. We just doing whatever we want here in the main method. We are setting it as an output, and we have an infinite loop. It's working. Whenever the interrupt happens, the code stops, and then it searches for the ISR, interrupt service routine method, and after searching for it, it searches for, or it tries to match the vector name of the received interrupt. Okay? If it did not receive a matching vector, it will not implement this ISR. So please try to write the correct vector, and then it deals with whatever data it has, and then it's done. Okay? And to configure our USArt, as we said before, we set our baud rate, and then the receiver through the second control register, and set the size of the data through the third register, and that's it. This is in embedded C, not Arduino. And that's it. Thank you so much for listening to this, and best of luck.